collection. And one of the reasons I began to study all this dense matter system is, of course, because of the presence of Mandu. And I began to collaborate with him about 10 years ago. And then somehow the subject suddenly became very popular after the work of Dam Han-sung. Although it was the work for not in hadron phase but in Coulomb plasma phase, I guess that the most of the puzzles of nuclear physics lies on hadronic sector rather than in QGP sector, I would say. And it would be very nice if we can do something in terms of a new viewpoint of view, so-called holographic point of view. And so why we do dense matter? Some motivating comment is that because something is there. For example, neutron star is there, and even heavy nuclei are all and should be considered as dense matter system. Yet, I mean, even lattice gauge theory, not alone the hQCD, cannot calculate anything definite in the case of dense matter. So this area is largely open to any kind of definite prediction or calculation. So because we can do something definite in terms of string theory, so I think we have definite motivation, but there is a caveat also, which is this new method is not talking about the real QCD, but an analog of it, because it is necessary to introduce a certain amount of QCD, supersymmetry, which is not absent in QCD, in order to fully justify its use. So that much understood. Let me just introduce some jargons. And the jargons is all familiar to you, but I first need to interpret everything in terms of the new language. So for D brain, I'm not going to introduce it. And so what I'm going to say is that the quark, first I begin to quarks. Quark is if we have, for example, some dp, dq system. For region is, let's say, p equal 3 and q equal, let's say, 7. Quarks are represented by the low energy dynamics of the string, which is connecting between these two. And the mesons are open string vibration, which is describing the vibration of this dq brane. And finally, the baryons. Baryon is a little bit more complicated object. In hQCD was first constructed by Witten, and it is the following. This dp brane has a so-called Ramon charge, and it has fluxes. And if you have, for example, some compact object which can wrap the orthogonal space, which is the transverse to the p brane, then there is a charge induced on this compact manifold, which is not allowed, right? Due to the Gauss theorem, on any compact object has a net zero charge. So in order to cancel that charge, we need to attach some strings whose endpoint can cancel. The charge of the endpoint can cancel the induced charge here. And then if you calculate the amount of charge which is introduced here is exactly equal to the number of the DP brane here, which we call as a color brane. So, and the number of the, so that in mathematical language, if you have a D3 brane, you have a 4 form, and so you have this derivative which is a 5 form, and if you calculate the flux of F5 on 5 sphere, for example, here, then it is its unit is exactly NC in some unit. Therefore, in order to so if there is a flux this much, then Chen-Simon term here is looks like let's say AT times F5. So that the integral of this S Chen-Simon is given by roughly NC times AT. So we need the string charge which is exactly the NC amount. So we need the NC strings attached to it. And then what should happen is that because this is attached to compact object, they cannot go very far. So this is confined. And we are living on this DQ brane. And some of them should be compactified. And we are left with effectively 5-dimensional world on here, where one direction is left over in order to play the role of so-called holographic direction times our old, 3+1-dimensional world. And the fact that they cannot go very far is the so-called fog confinement. However, this fog confinement is rather is actually in holographic hQCD is very far from so-called gluon confinement. So in order to introduce the gluon confinement, what you have to do is gluon dynamics is described by the so-called gravity dual, which is caused by, you see that if you have a large amount of the NC branes, then this brane deforms the space-time nearby, and that gravity summarizes the dynamics of the gluon physics.
So in that picture, do you need
heavy quarks. Yes, I will introduce those things later. But at this moment, please bear with me. So this is a little bit important, and you see that apparently this the gravity thing or gluon confinement and the core confinement has nothing to do with each other so far. But this is not the case. So how they are related? And that is a kind of rather subtle subject, but it turns out the scenario is the following. This object, which is just introduced by hand, should be examined actually by mathematics, whether such object is really existing or not. And the first person who studied that is Kallan, and is a student. And then they numerically examine whether such, suppose we have a D3 brane or some gravitational source here, and then you want to consider whether such a compact object which is satisfying the equation of motion. You see that any brane, D brane dynamics is controlled by action, which is so-called direct on indirect action. And if you examine equation of motion derived by this, then the equation of motion is satisfied by following configuration. You have here gravity source, and then there is a compact object here. And then according to how many strings are attached here or there, it has some kind of this kind of shape. And then it turns out that for the ADS, pure ADS 5 times S5 background, which is originally suggested background for the gravity developed and for gauge theory, such configuration is not stable under the perturbation such that it goes to this is a small, the less heavy than this one, and then so forth and so forth. So that if this string should be continued to there, then what should happen is that it goes to like this. Therefore, compact brane is not stable. So the point is that not only the gluon dynamics allows the variance in this theory. So it turns out that if you consider it's coming from my airline agency.
Another flight canceled?
Maybe. So anyway, so it turns out following is true. If gluon dynamics is not confined, gluon dynamics is not confining, then no baryon. So that is the consistency between the core confinement and the gluon.
That instability, for my guess is that instability is related to conformal symmetry.
Yes, it is.
And do you really need more time, or just the break of
Scale breaking. Actually, not only yes. If in certain sense, if you have a scale breaking by hand, for example, that is in the case of the hardware model, you can perform certain confinement effect. But not everything is confined. So because, for example, in that way, you don't get linear potential. For example, Wilson loop doesn't have the linear growing potential and so on. But for the Hadron spectrum, such introducing certain scale is equivalent to the introducing mass scale. So for that purpose, that's all. So
yeah, I think if you have scale,
if you have scale, yes.
then I think such configuration is possible in some ways.
No. Anything which is determined dynamically is not good. for example, if you have a pure D3 background, which is ADS5, and then you try to find, you have you excise a certain region and try to find such a thing, it doesn't happen.
Okay, so scale breaking is not enough.
That's not enough.
Actually, the scale breaking is very artificial to make, how can I say, to prevent.
No, that is by hand.
Yeah, there is shape of curve, so it's really artificial thing. But this shape of D5 ray is governed by real dynamics, comes from the DBI action. It's very difficult.
All right. So let me. Since I already explained the basic ingredient of these three objects, so let me mention about the more important this CFD dynamics, which I think is necessary for later purpose. So I think that here in this room, most of the people's top priority is understanding the chiral condensation or chiral dynamics. And also, but for this purpose, today's chiral symmetry is kind of a fictitious one. Well-known chiral symmetry breaking realization is given by Sakai Sugimoto, where you have D4 and D8, and here this one and this one is identified, and there is a D8 and the D8 bar, and the presence of a D8 means that we have a rotation or permutation between D8s, and that defines SU and F. F means the number of D8, and there is another one, SU and F. So that this and that one is all independent. Therefore, you have a left and a right independent symmetry. However, if you turn on the gauge coupling, I mean the string coupling, then the gravity dual of this many let's say D4 create some kind of hole inside the space-time, so that it cannot go through like this, but it should be connected like this. When this is rotationally all connected, so that from two brane and to one brane, so we have only one symmetry is left, so SU and F times SU and F. From here, we are breaking it to only diagonal. So that is exactly analog of the chiral symmetry breaking and strong interaction dynamics. So we accept that this picture is revealing some, it carries some truth. So furthermore, when there is a D8 and a D4, then the good thing is that the fermions here are all violent. Therefore, we can really talk about the chiral symmetry, literally. However, there is some problem here. Good. So, in terms of chiral symmetry, this is a perfect model. The problem is that we don't have a mass. Man Q is very difficult. Very difficult. So in order to say that, let me mention about how we define the mass. Mass in string theory is determined by the separation length of two branes. So this, when the coupling is 0, they don't interact. And then string length is identified as current Planck mass. There is several reasons for doing this, but the most intuitive reason is because this string is, I already said that this is representing, low energy dynamics is representing curve, because there is one brain, one kind of a brain, so there is endpoint index is following I equal 1 to NF. The other one is carrying other index, which I call C equal 1 to NC. Therefore, low energy dynamics of this string is carrying two index, which is represented by the field, and we have I and C, which is perfect for by fundamental, or this is not by this is by fundamental, but this is exactly the quantum number of quarks. Quantum number of quarks. So once you accept this length is the mass, then you see that mass term in field theory is psi bar psi. So in any Hamiltonian, kinetic term plus mass term like this. Therefore, if you have some full action or Hamiltonian, interacting Hamiltonian, and then calculate the derivative with respect to m, the result, if this is non-vanishing, that should correspond to psi bar psi condensation. Okay, that can be rigorously established in any theory. So the lesson is that whenever you have a separation here, okay, whenever you have a separation, we can calculate the psi bar psi by looking at the separation distance, how the separation distance is changing. Right? So here I introduced the just two non-interacting D brane, but if we turn on the coupling, and if we look at the many NC, many D branes, then space-time near here deforms, and that can give some force to here. And according to what force is there, it can bend upward or downward. And upward means it can be summarized as a kind of repulsive gravity. But there's no repulsive gravity. But actually, what's going on is there is the charge here, and this charge is repelling each other. Gravity pulls, but in such a special case, some special case for confining background, the charge dispersion wins the gravity pulling. But we just summarize it as a negative gravity. But actually, things are determined in another way around, which means that if the net force is repulsive, then we call it as a confining background. Okay, that's the definition of a confining background. So anyway, the important thing is that consider this confining background, then this pulled up like this. Then separation, so now you ask, what is the separation between this guy and that guy? It's changing here and there. So here is a big, small, and so on. So you define the so the separation is depending on the so-called embedding dynamics. But this shape of D6 or probe grain, or this is so-called flavor grain. Shape of flavor grain is encoding the dynamics of mass and chiral condensation. That is the one present wisdom how to deal with the chiral condensation, so-called chiral condensation.
This is not Sakai's model, did you?
Right, this is not the Sakai. The point is that here, if there is a separation like this, we can discuss the chiral condensation by using the dynamics of this embedding. So if you call this, let's say height as y, then let's call this direction as a rho, then of course asymptotically it is constant because it is very far from the effect of this. So that the y is some constant which we call as mq plus 1 over rho squared. It turns out that this falling is the 1 over rho squared, and its coefficient C can be identified with the psi bar sign. So at this moment, I give one comment here. In the presence of just one grain, we cannot define any chiral symmetry from the beginning. So although this is a psi bar psi, it's not really related to the true chiral fermion or anything. So nevertheless,
before discussing chiral fermion, how can we distinguish quark and antiquark in that?
quark and antiquark. So here you see that when there is a brain, we do have quarks. But if we in ADS-CFD, what is happening is by turning on the coupling and also by looking at the near horizon, I mean very near here, this brain disappears. At that moment, we don't have any quark. So the point is that if the mass and the, you see that although we introduce the quark and this mass at the zero coupling, okay, and once we identify this embedding dynamics with the mass dynamics and the chiral condensation, then it doesn't matter whether this is explicitly there or not. Although quark is gone, and we can still talk about the quark mass and also chiral condensation, so-called chiral condensation in this way. So that is one thing which is commonly accepted. But I said there isn't any chiral symmetry, real chiral symmetry in this sense, because there is only one kind of grain without anything else. No right-handed fermion, for example.
So the question is a distinction between quark and antiquark.
Yeah.
That's coming from the orientation.
But probably if you have antiquark is at this moment you can just call it this one or that one. But and once in any relativistic theory, once quark is there, antiquark is there. That is guaranteed. So it's not very much different thing form and antiquark. It's just orientation, as Shin said. But the more relevant question will be, what about the chiral fermion left or right hand? That isn't necessary. That necessarily introduces two different flavor grains. So, all right. So here, I said that now I'll come back to here. I said in Sakai's motto, introducing mass is very difficult. The reason is because we are working on 10 dimension, and this is 8 dimension, space 8 dimension. So time, including time, is 9 dimension, and we have only one direction remain, and that is already used to describe the one more direction and of the D4. So, and this D4 and this DA should always meet. There's no room left to be for these two branes separated. Therefore, mass is always jump. Therefore, you cannot discuss so-called GOR relation, right? Although chiral symmetry is introduced, chiral symmetry is good, but in order to discuss chiral symmetry phenomenologically, you need to be able to break it. That's the subtlety of the chiral symmetry. And if we cannot do it, and if we don't have any GOR relation, there is no reason why such a symmetry is introduced at all. So, I agree that we don't have any true chiral symmetry here, but nevertheless, I'm using it just to be able to calculate the chiral condensation.
So in the sense, what you're saying is that there's no sense of spontaneous switching.
No sense. No spontaneous breaking if you don't have any expressed breaking. That's the nature of the chiral symmetry.
We can also consider Yoga action symmetry. That is not related to the
Okay, now here let's come back to this scenario again. So this is a part of my apology that we don't have this true symmetry. But nevertheless, we do have a so-called one U1, which is relevant to discuss the chiral symmetry breaking here. So that is the called rotation of this D7 along this direction. You see that we have a 10 space-time, which is a 1 plus 9, and then this is occupying 0, let's say time 0's direction, 1, 2, 3. And then we have D7, which is 0, 1, 2, 3 common. So all the directions of this is occupied D7, but it has a transverse direction. 4, 6, 7, 8, 9. And among them we need 7. 1, 2, 3, 4, 6, 7, 8, 9.
There is 5.
5, yeah. I missed 5. Thank you. We need a precious 5. So we have 7 here. So up to here, D7 is occupied. This is D3, and this is D7. So we have 8 and 9, which is transverse to both D7 and D3. So which I call it as the plane orthogonal to this one. Okay. In this plane, D7 is nothing but a point. Okay. So in that 8 and 9 plane, D7 position here, this position is described as a 1 point. Somewhere here. So if we define this y to be identified as a radial direction, or we just simplify discussion by calling by rotating the axis such that D7 is passing this y axis, y1, y2 axis here. But anyway, the point is that if this height is not 0, then it is somewhere here. Okay. So this is exactly some kind of very similarity. You have a sigma model, linear sigma model, where we have a double hat potential, and then you have a degenerate vacuum here. Alright. So this circle, okay, is this spontaneous symmetry breaking correspond to rotating this axis. It doesn't matter where. So the non-zeroness of this mass correspond to, we have some vacuum expectation value at the infinity. Okay, but such thing, expectation value could be discussed anywhere, here or there or here, like this. Okay, so spontaneous symmetry breaking. So in the presence of MQ, is expressed breaking. So spontaneous symmetry breaking will correspond to, and asymptotically this goes to 0. So it goes like this, but it still has to pass, something like that. So that corresponds to, asymptotically, the mass is 0. So in this case, MQ, current from mass is 0, so that this is a kind of originally chiral symmetry could be restored. But if at the middle of somewhere, if this height is non-zero, then this is the situation where spontaneously mass, the expectation value is shifted to here. Okay, so that's the situation. So this is the chiral rotation. Chiral rotation in this case is rotation is replaced by x8 and 9 rotation, and the mass is allowed because we have just 2 more leftover direction, so that there is a tensor. So mass is MQ is allowed in principle just because there is room for D7 case. So that's the merit. So once we have such a separation, we can consider the chiral dynamics. And the chiral dynamics is nothing but how fast this slope is. So for example, intuitively, if this height is the same, right? This configuration, if you compare the two, this should fall faster than this guy, which means that chiral condensation for this guy is bigger than this guy. That's the kind of intuition you can have. So everything is a geometry, which is the strong point of the so-called top-down model. So now you have some flavor of what is the so-called chiral symmetry in this context. So the point of this discussion is we still have the GOR relation, Gell-Mann relation. GOR relation can be established.
You have that relation, you must have mesons and hadrons spectrum.
Yes.
Rather than this kind of things.
So what is a meson? I briefly said that meson is a vibration of this open string, and which is equivalent to say that it's a vibration of this D7 or probe grain dynamics.
Then how can that be related to this idea? You just mentioned meson like that. You just mentioned this one. For me, it's quite separate thing. But you just take that.
Okay, let me just mention how to establish this one. So I said that meson is a vibration of C7, for example, and then your question is how to establish GOR relation. GOR relation is a Goldstone version. Squared is related to Q bar Q, side bar side. And then F pi squared times MQ, something like this, right? There's minus conventionally. And then first, you need to identify what is the Goldstone boson, right? And the Goldstone boson is corresponding to what? And if you have the 8 and 9 symmetry, then this symmetry, this is a symmetry circle. This vibration along this symmetry cycle is this vibration mode is the rotational mode is the Goldstone boson. So you have a TBI action, and you have therefore you have a definite Lagrangian, and then you identify this mode, and then you calculate mass spectrum, and then you can establish GOR relation.
In that mass calculation, you need a side-by-side condensation here.
Oh, because we need to first, what is the vibration? Oh, sorry. First, what we need to do is we need to find out the shape first. That's the classical dynamics.
In DBI action.
In DBI, with the DBI action. And then once you find the classical embedding, then you need to consider the vibration of this shape. And that certain vibrational mode corresponding to 8, 9 rotation mode is the so-called Goldstone mode. And identify the pion more precisely, because this is U1 only, not pion, but eta prime. So this
Then how the MQ enters?
Oh, MQ.
Or
You see, MQ is entering as asymptotic distance. I here draw the MQ is a zero case here. This is the MQ non-zero case here. So what we are doing is this we need to vibrate this one along this direction, and that distance should be entering in the calculation, and that is the MQ, how MQ is entering calculation.
Even though you're using the profile, you just erased.
Which here, I said that if MQ is zero, strictly zero, then you don't have this guy.
That profile is a function of MQ. So if you choose one MQ,
Yeah.
and you have one profile.
Right. So you have for fixed MQ. For fixed MQ, you can vibrate it like this.
And how about the pi squared?
And for pi squared is entering as an overall coefficient of the pion Lagrangian. So once you have a DBI action and then reduce to quadratic and then read off the coefficient, and that gives you. So that is it will be. You see, there is a little bit far away to go, but basically f pi is the coefficient of a trace of whatever u squared, and 1 over f pi squared is the coefficient. This is a 4-dimensional Lagrangian, and what we have here is effectively reduced 5-dimensional theory. Therefore, you need to you have the 5-dimensional integral should be transformed to 4-dimensional integral. Therefore, transverse direction dg should be identified, and then this integral will give you the height after you do Cauchy reduction and so on. But anyway, that.
Okay. Then my last question is whether the m pi squared is proportional to the mq or side of side. The functional dependence. MQ is this approximation, or the profile gives exactly
This f pi, actually this f pi.
That's over vector, that's fine. But MQ dependence is linear.
MQ dependence is linear.
Is it strictly in the profile?
Yes.
Any kind of profile?
Because here, yeah, right.
That MQ is not height, but the height at the infinity.
At the end. This is asymptotic.
So MQ
So MQ is kind of independent of the dynamics. It's just current continuous, and it is not affected by gluon dynamics. So anyway, maybe more properly, we need to go a little bit more detail, but let me not spend too much because we have some goal here. So these established how to discuss chiral dynamics, so-called chiral dynamics, and also mass and the condensation and so on. So let me move on to the dense matter. Which is the central subject here. So if you are considering the so-called QGP, it's quite easy in some sense. Because in QGP case, it has a finite temperature, and also it should have a finite chemical potential. So you need to introduce the finite temperature and the chemical potential, but let me be very brief. So for the QGP case, you replace the core. Previously I said it is a kind of repulsive force. That's because we are introducing some repulsive gravity. But for the, to describe QGP with the temperature, we need to replace this one by black hole, which has its own temperature. And that black hole temperature, Hawking temperature, which is in ADS case is proportional to mass, total mass. And that temperature is identified by gauge theory temperature, Gluon's temperature. And also the chemical potential can be introduced by introducing charged black hole. Simplest way, charged black hole gives you not only the metric deformation, but also it creates, because it's a charge, there is a what? Electric field is created. So let ATB is the electric potential, and then electric potential at the horizon is said to be 0. At horizon is said to be 0. In order to avoid the singularity, and in that case, then AT at general distance R, near, especially when R is very far, is given by some constant times, let's see, R squared, or let's say some constant, let's call it Q. And it turns out that this mu, which is a asymptotic value of the AT at infinity, within the boundary condition AT is 0, that is a gauge fixing condition, and this is a gauge independent meaning, and this parameter mu is identified as a chemical potential. And this parameter here is identified as density. And actually, this is a very generic the situation. Whenever this is actually, you should compare this with the Y, which is the mass and the chiral condensation are squared. And this is a mu q mc, so they are dual to each other. Multiplication with mu times q is always the order of action, and the dimension of action here the same, n times c, and this is generally true for any field phi. And the leading term, if you expand it, there is a leading term, let's call it phi 0, and then the subleading piece, which so let's say A, and then there is R to the some power. And sometimes this identification here is not always constant, but there can be some power of R, and but the leading and the subleading is always interpreted as this is some, let's say, this is the if this is the operator expectation value, and this one is the some source. Let's see. Okay. So for us, these two are enough. So let me just let's not go into the detailed discussion of the AD's CFTBAG, and let's go to hadron physics first.
So you define the chemical potential and density.
Right. So this is the case. Now
my question is, in thermodynamics, if you are in chemical equilibrium, chemical potential and density is not an independent quantity. They are closely related.
Right. It's always.
How can you?
Right. So what they have to, what should be, how they are related is following. Don't consider this one. Don't consider this as something independent parameter. Okay. So if you calculate the action, then it is a function of mu and q, actually. Right. And then how you do is that if you identify mu as the chemical potential, density is identified the ds and the mu, roughly. And then d, okay, is for given d, mu and q is related. And it turns out most of the case, if you calculate this object, it turns out to be d is equal to q.
So it's a kind of unshell.
Yes.
So you.
Because yes, this is exactly the point. This is the initial. So all the fields are gone. Only parameter dependencies remain.
So actually, you first start with some physical quantity in terms of the density of it, then you can define chemical potential, and then you shuffle all the equation in terms of
right. So if you begin to from the beginning, if you interpret mu and q as a density and the chemical potential, you are derived to that question.
So the interesting thing is why the mu comes as a first term, and why the density comes in the form of q over r squared. So that's quite interesting.
Quite interesting. But
do you have any explanation for that?
No. But this is just a coincidence at this moment.
I have some explanation. Suppose that we have charge in the geometry. Then the charge makes electric.
So you are in 5 dimension or
I'm 5
3
dimension.
Sorry, just specify the dimension.
No, I'm talking about that.
Okay.
R is the fifth dimension.
The fifth direction. Okay.
Yes. And because your question is why Q appears in front of one power. So
density.
If we have density, it corresponds to some charge in terms of gravity curve. If we have charge in 5 dimensions, then we will have electric field along the R direction. So how many density we have is how many charge in the 5 dimensions. Then you can count that the amount of the charge by using cursor. You have to to integrate electric field. So the charge is proportional to the electric field, and the electric field is dr AT. So the pass down constant cannot be electric field, but the circumference can be electric.
In terms of charge, it's okay. But in terms of density, it's okay.
Charge
That's the question.
density is some dual of this charge.
How is dual?
No, there are many ways to talk about it, and there are two ways at least to talk about it. One is using the AT dictionary, but the other one is to use the so-called the global versus local the symmetry. I said this is the electric field, and then this is electric charge, and then I said that this electric charge is the density.
Actually, there is one.
And the density of one. And that is that there it comes that there is U1 symmetry. Originally, what do you want to do? What you want to do is we have a baryon, the conserved number. So that conserved U1 is which is a global symmetry, which is a baryon number. And according to AT's shift, that corresponds to local U1. Local U1 means that there is a gauge symmetry and the gauge dynamics there. So, it is inevitable that the global conserved number, which is a baryon number or baryon number density, should correspond to, in this local charge dynamics, as real, the local charge, electric charge. So that is the one of the understanding. But largely for me, the best way to justify, you see that this condition gives you mu is equal to r plus the square root of q. This relation, which relate the charge density or charge and the chemical potential, even from the beginning without any identification of whatever. But it is remarkable actually. I said it's remarkable that if you do this calculation, okay, it exactly produces this calculation, this result. For me, this is kind of very satisfactory and mysterious. Why? I don't know. So anyway, let's go to, so this is, I said that this is still in the presence of a black hole and the temperature. And what about so what is happening is that there is a brain, a black hole, and this is a brain, and then this is there is an open string connecting this horizon and the D7, and then this is a quark. This is a quark picture, which means that we are describing the chemical potential for the deconfined phase. Deconfined phase. Now we need to introduce the situation chemical potential for the case of hadrons, which is so you replace it by confining force, and then you have upward bended brain here, and then you have now trouble because quark cannot touch here. So you must have something which can accept this. So what I mean is, chemical potential is largely, let's see, asymptotic behavior of the electric field. And then I say that there is electric field here. There can be electric field on this brain. Okay. The problem is that we need some charge density here. And the charge density is provided by some quarks or baryons. If it is a quark, there must be string, and there's nothing. So you are in trouble. So resolution is that we have a baryon vortex, which we introduced before. So there is a baryon vortex. For each baryon, NC of strings can end here, so which can provide the A with the electric field. And then you can still talk about the chemical potential. in that way, we can introduce the the density. So the point is here. The point here is that the density here, this density is a density of what? This is a density of a baryon number, and which is provided by clock or baryon. In this confined phase, these things should be provided by baryons, which is fermions as far as the NC is open. So you need now if you want to consider the mathematics solvable, then what you need to do is so you see that this direction is transverse to our space-time. This direction is our space-time. So each point here corresponds to, let's say that the brane configuration is something like this. This is a brane configuration, and then there is a D4, D3 core or whatever, and then for each the baryon vertex there is a NC strings there, and then here, there, and like this. So that's the usual configuration of the baryons in this setup. But the localized baryons here and there, like this, is very hard to treat. So what you do is you smear this situation, smear this along this direction. So consider what? So-called homogeneous baryon distribution. Okay. Maybe Changsun can introduce some chiral density wave here, but we haven't done it. So anyway, if you consider this uniformly smeared baryon distribution, then calculation is doable. And so the physics is the following.
So let me ask one more question. So at the left-hand side is the confined phase.
Yes, here confined.
Confined. So densities, if you're right, then density is well defined there.
Yes.
Here, what is it?
So here there is A, and then there is a charge according to how many charges here.
Charge is on the where? On where? Here.
Charge is and here introduced by the string endpoint here, and then the same story. Charge is here, and then electric potential, and then there is a chemical potential as a tail at here. So it's the same story. The only thing is that there is a canonical place where AT is 0. Here you need to introduce some position. It's anywhere, but it gives different gauge choice. You choose center where AT is 0. The same thing. Okay. So you do have still Q over R squared. Now you have plenty of electric charge, or which means the dual charge of the density at infinity, which means our world. Now, you need to do what you need to do is you need to determine the shape by this pooling. What is the consequence of the dynamics? So, because this is pooling, it is bent like this, and this is also pulled like this. And what you need to do is you need to minimize the action. Okay. So the minimization is arrived by considering zero string length. It's true that B brane is always lighter than the fundamental string. That's the rule. So actually you minimize the string length zero. And then that is the configuration, equilibrium configuration. All right. Now you first, once you determine this by what? First, you need the force balancing condition. balance condition, which means the upward force and the downward force should be balanced. And the second one is you need to minimize the energy. Minimization gives this kind of point of contact, and the force balancing condition determines the location of this position. So once you determine such a configuration, by the way, this method was developed by Yun-Sung and myself, and then applied to various situations. So the next comes now. If you want to consider, for example, Brown-Rowe scaling, which is saying that the
is this the only way to address this problem known so far, or are there alternatives?
So far, I should say this is the only way to discuss the density in hadronic sector. Period. No other way. So MV, what is the MV star? Vector the vector measure inside a certain density. Let's call it some density here. I said, in D7, for example, some direction of the D7, for example, 0, 1, 2, 3 is along the D3 direction. So there is in D7 there is a vector field A mu, which count mu from 0 to 7, so 8 component of a vector field. And also there is a transverse mode along this direction. So there is 8 direction. The transverse longitudinal, and this one is the this is not so-called vector version. This vibration is also called scalar. Okay, scalar. So there are a few scalar. So for example, y is a scalar. So unlike the Sakai-Suzuki motor, we do have some scalar. So there is a room to discuss sigma here.
What's the energy mass scale of that object?
Mass scale of the here, okay. Whatever it is, all the mass scale is controlled by so-called MKK, which I didn't introduce so far. But you know what is MKK. I will do it later. But anyway, let me finish it. About how you calculate the measure spectrum. Measure spectrum is a so there are some scalars and there are some vectors. Among these D7 vectors, there are A0, 1, 2, 3, 1, 2, 3, which is really so-called vector, which we can identify as rho measure and so on, rho and omega and so on. Here, transverse direction for this is also identified as a non-vector. So this is extra, vector. But these extra vectors are supposed to be along the convective by the direction or radial direction. So, for convenience, not because it is not important, but because just for this is all so-called certain class of Carolak line. And just forget about it. Okay? And then this is really those four-dimensional vector motion after Carolak line. And then you can identify vector motion. So which is so conceptually everything is easy. Vector motion is some vibration along spatial direction. In this picture, this is a space-time direction. Along this direction, vibration is the vector motion. So Marcus' question is how it depends on density. That was the first question he raised now how many years ago? Huh? Many years. Many years. 90, right?
90 years.
Right. Even before. Yeah, right. So it's 19, it's only 20 few years, right? It's amazing that the question was raised more than 20 years ago, and still, and it's indefinitely. So now the question is, what is the density dependence of a vibrational mode here? Okay, and then the rest is calculated, and those calculators are 강현조 and 윤석서 and so on. And then let me give you the answer directly. This is the density dependence, density, and this is the m star rho. And then it happens here, it is a flat. And then it quickly turns its direction, is almost linear. And then it doesn't come like this, but it turns like this. And then it's not very clear whether it's saturated to somewhere or to zero, but it looks like it's saturated. Am I right?
One question.
Yeah.
So the Q, on the right hand side of the black hole, look where the density first introduced.
Yes.
Q of R squared. Q is M.
Yeah, Q is N.
Yeah, Q is let's say
N.
constant times n.
So that's the N. Here.
Yeah, right. So that is
For large N is a larger Q. So we don't consider back reaction.
good, very good. So in any of this so-called probe-brain approach discussed here, we assume that this number of Lie is small enough so that gravity, background of gravity is not modified. But that is purely approximation. And actually, that question is good because I am speculating that this kind of behavior might be related to probe approximation.
Well, that's contrary to what HYU is saying. You say the larger the Q, the less back reaction. Is that what you're saying? You didn't say that?
I just asked.
Oh, you just
What the back reaction. And then, yeah.
Well, no, you said the back reaction, the approximation of doing the probe approximation is good, you said.
So anyway,
So one more question is,
Yes.
how about mu dependence?
mu.
So you have two parameters.
No, these are related, as I said.
Oh, okay.
Because
Okay, I see.
mu is GDP.
So if you vary Q, then mu is also a function of Q.
Yes.
Okay.
So it doesn't
So-
matter whether you work
So
in canonical or
can you
dynamical.
draw this mu
And Q.
versus Q?
Yeah, it's a little bit complicated.
No, in this case, in this case, mu is grow as Q increase, but not linear, but there is some special
Not
shape.
linear.
But
So, yeah, because
monotonically increase.
so here it is you see it's linear, but here is more complicated. It's not linear, and it can be very complicated actually, according to the situation. Mu-Q diagram is actually essentially equation of the state.
Yes.
It can be only worked out by computer, and it's not obvious at all. It actually shows us many very, very complicated subsectors and phase transitions and so on.
And that can tell more about the equation state
Yes.
rather than just
So
Do you have any indication application of first order phase transition at very high density. So it's just monotonically going down and
Right,
down.
so this is a completely different story because here, what we are saying is here there's just a few number of things, and then few number of branes, and then we have a small vibration. That's what we are looking for. In order to look at phase transition, when this top-down approach, so-called top-down approach, where you use a higher dimensional brain, is not good. Because I have experience now almost 5 years ago, 2007, that one of my collaborators, Yamnan Kim, and also Yunsa, also. Here you consider the so-called phase diagram where you have mu and t, and then in this Lagian series, it's always just first order. First order transition is happening like this, and then it goes like this indefinitely. Here there is a small density dependence here, but basically this is what is happening. On the other hand, if you consider back reaction of gravity starting from the this is in most of the phase diagram coming from top down, or instead of top down maybe global transmission. But this goes down actually like this if you consider the back reaction.
So within proper approximation, chiral symmetry never restored.
No. No. So in this probe approximation, the density can do very little. It doesn't affect much about the system. So there is no way chiral symmetry can be broken in this top-down approach. Yes.
It's quench approximation. So that is language.
So now I here for very large density.
Oh yeah, but I mean, even quench approximation that is the large density limit. There is a common Newton theorem which says that chiral symmetry is broken. So if chiral symmetry is more than is broken,
but
then must
at
have
high density, the question is whether it should be restored or not.
well, if it's potentially broken, the theory must have a restored phase by definition.
So I'd like to have very intuitive
Understand.
reasoning why no chiral symmetry restoration at very high density.
Right.
So how can I understand it? Just intuition.
Because that chiral symmetry restoration is maybe related to the some gluon dynamics, but in this case, this geometry does not change from this.
Yeah, that's
program.
the basic reason. You see, let me show you what is going on. So chiral condensation, right? Fusion chiral condensation is given by the slope here.
Okay.
That the chiral symmetry, chiral condensation going to zero means that this is actually going down zero, which means it's like flat, like this. Which means it should be able to go down like this. That is the case actually for if there is a black hole here. But for the repulsive geometry, that means for confining geometry, this is always, whatever you do, even for the zero quantum mass, this part should go up because it's pushed up. So there is a tail like this. So it should, be non-zero anywhere. If actually, this is a kind of electric region why, actually, let me see. So what about the density? So you are asking now, what is the effect of the density, right?
Yes.
So density effect is the following. The density is here, there is a baryon vortex. there is a string here, so it is pulling. So the more charge here, okay, the more strings here, the more pulling. So it should pull down like this. So at first, what is happening is that because this is pulled down, it's going down like this. You see, so that it first drops. Then what happens? If this is pulling more, if there is more density, then it's going down more rapidly like this. And then if this is steep, then it should it's just nothing but just a kind of rocket with a certain theta. Okay, it's a kind. So if this theta is smaller, then it should go up actually more. You see, because it has to go up, and it should fall more. That means chiral condensation actually goes up. So this is inevitable. I mean, in at least for this probe approximation of a calculation, what is happening? Chiral condensation versus density. At first, it comes down slightly, and then comes up.
So this dramatic drop in your medium raw meson mass is nothing to do with restoration of chiral symmetry.
That's just the point. Here, it goes down, but it's not related to this so-called chiral symmetry. That's what Mangi was briefly mentioning the other day. So, anyway,
Q가 Q 보자.
you see, according to the wisdom and this chiral condensation, Q bar Q and F pi is proportional to each other. And according to my collaborator Ismail Jahed, there is some reason why it should be. And the F pi is proportional to, let's say, this here. Basically what he says is that it's larger than that. And then F pi is, there is some repulsive part, and there is some attractive part. And the problem is that at large n limit, and this is vanishing, while for n equal to 3, this is the dominating part. So we are losing the dominant piece by taking the large n's limit. That's why inevitably f pi calculated in this model is always go up. I never saw any other. F pi time component is always go up.
I'm not lost. So, but before you told me that F pi is as a result of the extra dimension 4 factor. When you explain the GMR relation, you told me that F pi is calculated as an extra factor.
Right. You see?
How now?
Right. So now the question is whether GY relation hold for high density, finite density, right? Question is that one. Is that right?
Yes. So GMO relation means that m pi square is proportional mq times psi q by q divided by f pi. So, right.
C.
Yes. So now you relate f pi with C in the expression.
Right.
Oh, I see.
You see that this is going up, this is going up.
F pi is also.
Yeah. So now you can still ask whether the whole thing
do you know how to,
what is happening.
You know, in your scheme, you know how to calculate f pi.
Yeah.
Right.
And that is calculated actually.
In that configuration.
Yeah.
I see. So that depends
Also
on,
goes up.
that depends on Q. Okay.
Right. Both depend on Q and the density. and both are, but they do not, strictly proportional to each other. So there's tendency, the tendency is correct, but it's not directly proportional. But anyway, if this is true, I don't have I will not bet my life on here, but
Which
there
one?
is some
Left hand side or right hand?
whether this is really going on, but that is a very, the kind of convincing story,
Yes, convincing
which I learned from this man.
Which story are you convinced with? Which story are you convinced with?
No, at least what I'm saying is that you see, the reason why 20 years, after 20 years, nothing is confirmed or disproved or anything theoretically.
Well, I wouldn't say that. That's
Because you don't have any definite calculational scheme. And here, I agree that I don't know whether this is the correct way to calculate or not. But definitely, this is a reliable calculation, actually. It can be completely wrong because the model is wrong and we are calculating some wrong object, wrong theory, but the calculation itself is reliable. Okay? So, if this is not correct, then we can search other models. Therefore, we still have some definite, way to go. On the other hand, in usual conventional method, you don't need to ask, because this is strongly interacting, you need to calculate the corrections. And one loop is more important, the two loop is even more important, and so on. It's guaranteed that to be, your activity is nullified. You don't trust your own calculation. As soon as you need to give a correction. But here, the whole point of the ADS-CFT is that just we assume that we don't need any correction.
Except proof approximation.
There are such things. Yes.
And then the one more question is, could you give us the scale where and the normal nuclear density is located?
Yes, great question. And it depends on which data you are using. And then here, there is two parameters we need to fix. Very good. There is lambda, which is G squared so-called proof parameter. And C, this is Yang-Mills coupling. And then there's another one is the NC cell. So I'm sorry, MKK. And MKK here is fixed to be 1 GeV. 1 GeV. And the lambda was fixed to be about 2.7, around 2. Now here, this is some difficulty here when we talk about the phenomenology. Because you asked question, and you mentioned it briefly. All this ADS-CFT is valid for large n, and strictly it is valid for large NC, lambda goes to infinity, such that the G squared NC is big but finite. Okay?
No, wait a minute. Where NC is lambda.
I'm sorry.
Lambda over.
I'm sorry.
Lambda over NC. Lambda over NC, I guess.
I'm sorry. No.
GS.
I'm sorry. I was completely mindless. Lambda is GS times G squared NC, which is big and finite. Which means G itself should be small. Now, in the case of the, so what you need is for D3, D7, there is a request. You see that the original ADS-CFT is the string gauge theory duality. In order for the string theory to be reduced to the gravity, you need some request that this so-called the ADS radius R, whose square root is given by square root of lambda times string length squared, which is called alpha prime. Well, let's see alpha prime as squared. This must be much bigger than ls, first of all. And this requirement is because you have some ambient space, ADS space. Originally, gauge theory is dual to string theory inside. Okay. And then, if this string and this string size and ADS size is big enough and comparable, then we need to describe string theory itself. While if this is a kind of very small, then you can approximate it as a point-like. And point-like means field theory, which is gravity theory. So, for the gravity dual description to be valid, you need this description. So, this one, therefore, I'm sorry. LS squared, which means that both LS, that means that lambda should be very big. However, you also have some requirement that the let's see, NC itself, G squared itself should be small enough, and this must be small enough. If you really strictly require this one, the problem is that you see that this G squared is lambda over NC. Lambda over NC. And this is supposed to be smaller than 1. Okay? So you are in trouble because lambda, this means lambda is smaller than NC, and the lambda is much bigger than 1. And then NC, in phenomenological application, NC is supposed to be what? 3. So that's the so you are in trouble. So, but this large NC is always even from the 70s at the beginning of the period and the invention of Tooth. And the large NC, you calculate everything large NC, and you just put NC equals 3, and it's supposed to be very good. Okay, now the problem here is that if that is the case, lambda cannot be very large, and then the gravity approximation is in danger. So one of the things is that instead of looking for very detailed the phenomenological the value itself, you need to work in the validity regime, which means with a large NC and with lambda is enough. So that look at how in the reliable regime, how the theory is predicting, and then you try to just extrapolate the validity to the case phenomenologically interesting region. So that is the attitude I think we should take. But this is common to any application. It doesn't matter whether it is a D4, D6, or D3, D7. Any hQCD have such limitations. So I would like to say that this description and application of QCD and hQCD is good to discuss the general behavior, but it may not be very good for numbers itself. So even in the case of Sakai-3 model has maybe this case 20% the validity the error and so on, but this is just coincidence, and I don't have a very much value in that number.
So if I just say that cut C of C versus N, the right hand corner of the side, okay, so that there is some minimum point. If I choose that point as a 3 times normal nuclear density, that is fine for you?
So you mean that?
Yeah. No, this one, no.
So,
Okay, if
so you mean the your idea is scale
yes,
theory such
yeah,
that.
so, and I choose that 3 times degrees.
Right.
Is it fine?
Phenomenologically it should be fine. So, but I mean, in order to do that,
So you don't have any scale?
yeah, right. Then we need to fix the. You don't. We should not fix the NG equal to 3. So actually, that your comment is exactly what I would like to address. This NG. We should not restrict this kind of reasonable small number. Okay, now I have described the roughly what's going on in hadronic sector within this. But preliminary, also here another remark is that this is also very much in model dependent, I would say, and it will not be surprising that if you find a model where the C really go down to be general, because for some model, so the dominant piece is killed out by large NC, but some models it is balanced by flavor effect and so on. So what I am seeking for at this moment is instead of this top-down model where we have some total approximation limitation, so probably with the bottom-up model where all the scalars and gravity together with the vector is coupled together, I'm hoping that it just goes down to vanish. And the preliminary calculation says that it is like that in the confined phase, but we haven't done any calculation for confined case. And with this much, let me just off this topic. Any question?
In the deconfined phase, you mean you calculate is not equal to 0?
It's not necessarily 0, actually. Because deconfinement transition can be lower.
Oh, yeah, sure, it could be.
Yes, should be separated. So
Yeah.
there.
But I mean that infinite density. The infinite density should go to 0.
Yeah, but all this calculation and the confinement transition makes the system very much different. So geometry is suddenly changed. So that's why it's supposed to work with the transition. And while what we are interested in is the chiral dynamics in that the confinement phase. And, that calculation can be totally different than this one. But the interesting question is what is happening if you include the bending action of gravity in confined phase. That is really interesting in hadron theory.
Maybe if you have a large enough barrier number, then it will collapse into a black hole.
Yeah, that's the people expect that to see some dynamics is very hard.
So anyway, let me, how much am I allowed to go more?
Well, you're bound by 4 o'clock.
By my class.
We are hoping that you are bound by
myself.
Anyhow, no, by yourself. You only have 30 minutes. Okay, continue until you have to leave.
May I just ask one more question?
Yeah, sure.
So you have computed mass spectrum of low meson and high intensity, and in that case you had to impose some boundary condition of the oscillation inside the.
Very good.
And now the descending attached to the value boundaries. So now I'm interested in what kind of boundary condition you use.
That's actually a very excellent question. And there are many things I have to mention, but I just, as usual, I just describe punchline. So you see that there is a meeting like this. And actually, right, there are 2 approximations actually. One is if you allow to oscillate this guy, there is a back reaction to this oscillation.
Right, so it's a kind of flat direction.
Yeah, right.
And otherwise, if you fix this guy in this direction, alright, then we have some unreasonable spectrum.
So you can move horizontally and vertically.
Yeah, not vertical.
Not vertical.
So,
What about for the gauge field? Gauge field, because the vector is also. No,
gauge field is living here, right?
yeah, but the oscillation sounds it's a higher condensate. Because the shape of the oscillation sounds.
Yeah, right.
So,
Then, according to which mode you are
yeah.
calculating?
So now I understood about the signal.
But the chiral condensation is coming not from the oscillation, but overall shape.
Yeah. But I'm asking about the vector method. No, in that case, you are dealing with not the oscillation of the shape, but the oscillation of the gauge field.
Oh, no, I mean,
Some
actually, you see,
our direction.
Yeah.
It's also perpendicular to the variable.
everything is a geometry here. Even gauge field fluctuation, this is just a geometric fluctuation along this our direction.
Anyway, no boundary function was used.
Yeah, everywhere. I mean, okay. So, but and also we didn't calculate the oscillation of this guy because we don't know how to. Anyway, maybe later. There are some discussions here, but let me skip it. Now, the other topic. So let me just finish this part and nuclear symmetry energy. So everybody knows what is nuclear symmetry energy. So let me skip the whole motivation and so on. So basically, nuclear symmetry energy is that if you calculate the energy of a nucleon, some system, then there is a piece. There's a piece which is a proportion to volume or area, and then size and so on. There are pieces which is proportional to difference between proton number and the neutron number. And then it's proportional to P minus n squared because we are requesting P and symmetry, at least for the nuclear. So and if you neglect the electromagnetism, and the definition of the symmetry energy is roughly coefficient of the P minus n squared, maybe it's better to divide out some P plus n squared so that this is dimensionless number. Or maybe the same as the energy. This is energy and this is energy, this is normalized in that way, but anyway. So the way to calculate that is so P is N UUP, N is UEP. So such a isospin difference is reduced to just one pair of difference. There are some difference in different parts. So you see that if there is a baryon configuration in the dense media, which is described by this situation, then we already identified that if there is one kind of the parts, then this is just one embedding. And if there is another, so let's say this is a B kind. If there is another thing which is a little bit different than this, then maybe there are things like this. So that maybe this one is U. Okay. So now, whether whether you have this shape or this shape is determined. You see that this way the configuration is very D-brane configuration is entirely determined the boundary condition here. This is the angle theta, shooting angle theta, determines the difference between this configuration and that configuration. And it is possible that even in the case you do have a U and D even degenerate here, you still have the possibility where you have you arrive at the same position without having the same. So even in the case U and D degenerate, you still have the configuration where two brane can arrive at the same point. Okay. So if when this S2, for example, is the infinite, for example, then what happens is that you are not allowed to have a different number of quarks here and a different number of quarks here, so that the S2 will be infinity in that case. Let's see. So the idea is that the difference in number of so what is the difference between the energy dependence on P minus n, the difference dependence of the whole system is identified as this coefficient. And the difference in P minus n is reduced to difference in the quark number, Q1 minus Q2 square. The same thing can be written as S tilde, as a coefficient of the number of quarks, which is ending on here, and the number of quarks ending on here. So that's the idea. And if we can have a situation such that there is a pulling force, upward force, which is provided by this one, and also there is another force which is provided by this one, and that two force, F1 plus F2, is matched by the downward force determined by the density here. Let's say D4. So this is compared to D4. This is let's say this is D6, and this one is another D6. And this is called D type. This is the U type. So in nuclear metal, and the D core and the U core is supposed to be almost degenerate. So that's why we consider the same height. And then what you need to juggle is that you find two different angles which can match the downward force, and that will be determined by the fixing the number of Q1 plus Q2. There is a constraint that Q1 plus Q2 is the original total density of the quark. And under such a constraint, you don't care whether energy is minimized or not. You just calculate, okay, the configuration where Q1 and Q2 is allowed to be different, but it should match the force balancing condition. And then you calculate the Q1, Q2, and originally the whole energy will be function of Q1 and Q2. However, the thing can be written as a the thing two piece, which is a Q1 plus Q2 dependence, and the other one is a Q1 minus Q2, leading to square dependence. Right? Because what you do is you calculate the coefficient of this full function. You calculate the epsilon and the energy as a function of Q1 and Q2, and then extract the dependence of Q1 minus Q2 squared coefficient. So, and that will give you the symmetry energy S2, and then they can be converted to S2. And the final result looks like following. This is the density, and this is the symmetry energy S2. So the question is the following: according to the model, it can be happening like this, or it can happen like that, or it can happen even like this. And even for a given model, according to parameter, it could give this, that, according to your parameter. So that means that theoreticians do not know anything what will happen for large density. And so the claim is that in this setup, the behavior is the following. It goes like that. And then this here for small, very small density, it looks like square root density. And we know why it happens by calculating TBI action in the limit of the flat embedding. If you neglect the details here, then we can actually show that TBI action is exactly square root of density. And very surprisingly, even for very large n, the behavior doesn't change much. It is slightly deviated, but it's very still gives square root. And if you use a non-relativistic Fermion model, then this behavior should be this is coming to n to the to slope. However, our model predicts the square root, which is a different non-relativistic. So that which means that probably this system is describing this strongly interacting system is another kind of independent weakly interacting non-relativistic particles. That is the indication of this skill and
even at low density, where presumably free non-relativity particles.
Because it is as far as they are strongly interacting, you never know. It doesn't matter whether it's a very high density or in the small. And small means what? Few particles.
Yes, since you don't have scale, so
Oh,
you can't say
yeah.
anything about it. Just say that.
There is a scale which is provided confinement scale. That's the only scale here.
So
So in all nuclear models, the large density curves and then goes down. Every one of them. So I don't know the reason why it happens.
Go down?
It starts going down. And large density goes up like this, and then they all go down.
You mean here?
Yeah,
Like
yes, they all do. So I don't know. I mean, it falls. They all fall.
They all fall.
Yeah, they all fall. I have never seen any curve which goes up. For sure.
Oh, I didn't know. I looked at the Bauan's paper.
Right, but then
Yeah.
but then they didn't.
Where they claim that I can go even like this.
No, even like that, but it goes up.
Really?
Yeah, it turns around and then.
No, I don't think there is any model which is valid in line.
No, I'm not saying that they are valid. They are all extrapolation of nuclear models,
But
they all go down.
if it is going like this, how you can read? How can you extrapolate like
Yeah,
this?
well, it does something like that. That's the way it goes concave up and then concave down.
Anyway, and this model also, I think, is not very valid or very large density because of the global fluctuation. So
Furthermore, at small density, you usually like that and say, well, that's consistent with the observation. That is totally wrong. Small density, what happens is that the clusters occur. The experimental series, clusters occur, and then what happens is they just flattens and then.
Alright. So anyway, you see that we have made some homogeneity approximation,
Oh yeah, of course, yes.
which is invalid for very small
That's
density.
it, right.
So I think that therefore here and here is cut out. So this is one. It's not something very proud. I would say.
What is small n? I guess it's a density of something. But it's
Density of a baryon.
density.
Yeah, baryon density. I'm saying that this region is not truly valid because of the smearing out approximation.
So now we have two different charges, baryon charges and isospin charges.
Oh, isospin charge I neglected. I didn't count isospin.
I mean, but the,
okay.
The number of U and the number of
Okay, right.
different. So you
It is you can consider isospin.
Right. So
But
I'm asking.
I didn't consider any group theoretic.
But so you draw some graph. So I guess you have fixed isospin charge at some particular value.
Isospin charge? No. We actually, you mean for any Q1, that's what I'm saying. For any Q1, Q2, okay, which satisfies this constraint, you calculate the configuration for given Q1 and Q2.
So now that big Q is equal to N,
Right.
N is the proportion of Q1 plus Q2.
yes. Then I think you have fixed something.
You fix the total nuclear density.
And actually,
The limits should be constant.
yeah,
Q1 is a free parameter.
yeah, here, but
What is the free parameter and what is the fixed?
Q1 is a free parameter actually. You are just changing Q1. Okay.
So the horizontal axis should be Q1.
No, the horizontal axis is just total. You see that okay. So things are all right. Good. Thanks for the asking the question. So this one is depending on this is different number of
Right.
This is the density. These are our so you see that there is a N1 and the Q1 is a N1 and let's say Q2 is N2, okay? And then the whole thing depends on N1 and N2 separately. And the N1 plus N2 is fixed. And then you can expand the things such that as a function of N1 minus N1 as a function of N1 and N2, instead of using this N1, N2, you can discuss the thing in terms of N1 minus N2 and N1 plus N2. Okay?
So you
And then you expand this guy, and this is the leading term over N1 minus N2.
Actually, there is another one axis there. This is
Yeah.
which N1 minus N2.
But since you are considering only the say Hadron, on the first contribution in the expansion,
Right.
the coefficient is a function of only the total charge.
Yeah, right.
This is, and you draw that coefficient.
That's right.
in the-
This the coefficient is the
I see.
function of a total charge. This total
Okay.
density. So that is the density balance. And then I have a 5 minutes left. And then maybe anyway, and good or bad, this is the so far the best we have at this moment. And then this year we are going to discuss about the fully coupled system where Bang reaction is fully encoded. So stay tuned.
That should
Thank
be,
you.
that should be the great. Well, you have 5 minutes to answer questions, no?
Yeah, I do have 5 minutes. Still
All right.
wait 5 minutes.
Did you study property of interaction? Is that
Property of interaction. All the interaction is supposed to be included here. That's the picture. Because you see, this balancing condition is a condition of the so-called describing the interaction.
Yeah, and this is the calculation after averaging out for intensity. But first I want to know, let us compare two
Nuclear interaction. Then to do that, we have to break this smeary picture.
Yes.
So we have
Yeah,
to solve
right.
Before going to finite density, that's the first calculation. Yeah.
So you see that this is a kind of a mean field.
Yeah, I understand.
Right. So I mean, there isn't any local vertex interaction here. So everything is supposed to
we
be.
can,
Uh,
but not easy. Because for you, we can solve some single variable vertex
That's
solution. But in that case, we have to solve partial differential equation.
No, I think that this is pointless actually. I mean, if you begin to separate the whole thing as an individual thing, then we are losing the game. You see, the point is that there's a dense matter system. But all we have done is the whole thing as just as one object. Okay, that's the spirit. If you divide the whole thing into separate thing, then we need to be able to, first of all, we need to be able to separate this individual and also interaction between them. What I'm saying is that in strong interacting system, there is no clear-cut division between particle and the medium and interaction. They are all intermingled. Maybe there is no, the nucleon inside the nuclear metal.
My point is, okay, so to understand what kind of matter is discussed, we first know, we first have to know what is the property of single nucleon and what is the property of interaction. Okay? And then we understand each property.
That is a traditional approach.
Yeah.
And what I'm saying is that 50 years of the experience of nuclear physics show that that is hopeless project. If you divide things into just the nucleons individually, then you need to calculate full interaction. The calculation of the interaction in nuclear physics, I would say, forget it. You can't do it.
Or in this way.
No, this is the kind of the scheme
I mean, that's,
where things we do not separate
that's,
into the individual particles.
that's not quite right to say, because people people have been computing
Yeah.
many body interactions using the Monte Carlo techniques and things like this.
Yeah.
And they have computed out the mass number 56.
Maybe there is some computation, but whether it's the trustable is another question.
The only way you can see is if you could
No, the problem is the following. This is a very important question actually. And in many body theory, if the things are weakly interacting, then so-called Fermi liquid theory or quasi-particle picture is correct.
No, the Fermi liquid theory starts with a very strongly interacting system. That's how you get to the Fermi liquid fixed.
Right.
Yeah.
Okay. But that is possible only when you find some quasi-particles which is weakly interacting. Okay.
After.
Right. After all normalization and so on, you assume that there is some quasi-particles which are interacting very weakly.
Yeah.
This is the picture of Fermi liquid theory.
Right.
However, we don't know what that is in nuclear physics.
What Fermi liquid is? People know. I mean, people have been doing Beta Bruckner and all these people have been
So whatever. Okay.
No, what I'm saying is that's not. I think it's wrong to say that. Now, if you say, well, it's difficult, I agree. But lots of things have been done.
Sure.
Yeah, and they started with a two nuclear interaction, and they built the framework in which they do many-body calculations on the computer.
Okay.
They get the results which are really experiment.
Let me say.
Well, that's what they're doing.
No. Let me say it this way. If you consider two nuclei, okay. Yeah, you can separate it, and then although you cannot calculate the interaction fully, you may begin to calculate something, and then you may postulate some effective potential between them.
You don't
and so
postulate,
on.
you compute. You don't postulate.
Okay.
You compute, and then of course there are other renormalization group arguments and so on. You can do that.
But what I'm saying is that for any calculation in nuclear physics, you really need to calculate the whole loop. As soon as you separate particles, individual particles, and then interaction between them,
you calculate the loops.
you need to calculate the whole order.
Oh,
That's the request. And any calculation which stops at 1 loop, 2 loop, 3 loop is bullshit.
No, doing the loop calculation is a bullshit.
Yes.
That's the wrong way of doing physics.
There is no way to avoid such a calculation. As soon as you separate the nucleons to nucleons.
No, I disagree. You can't argue it that way, I mean, if it's a bullshit, how can you start making it? Okay, well, thank you very much.